Welcome to the latest in a series of webinars produced by volunteers from the Cambridge Museum of Technology. The museum was founded 50 years ago with the intention of preserving the building and machinery from the old sewage pumping station in Cambridge, and to act as a base for exploring the wider industrial heritage of the city. Our mission is to enable as many people as possible to explore, enjoy, and learn about Cambridge's industrial heritage. We recently completed a major multi-million-pound redevelopment in partnership with the National Lottery Fund and Historic England, which provides modern visitor facilities and exhibition spaces and allows the museum to run a varied programme of education and community programmes, as well as family events. The museum relies on a dedicated team of staff, volunteers and trustees, and we're always looking to add to our team of volunteers. We welcome people with all skills and backgrounds, so if you can offer your time and expertise, please contact us via the website. Today's webinar is free, but as an independent museum, we rely on the generosity of our visitors, both in person and online, to maintain and develop our operations. So please consider supporting us with a donation or sign up to support the museum through your online purchases.
Hello, I'm Pam Halls and I'm the curator at Cambridge Museum of Technology. I'm really delighted to be able to announce that the museum will be opening again on July the 12th. I'd like to thank all of the volunteers who have helped over the last couple of weeks to get the museum safe for the public to come on site again. I really look forward to welcoming you to the museum over the summer. If you would like to book a visit, you can book a visit online. Go to our website, www.museumoftechnology.com, and you can book a 15-minute time slot. You can also just turn up at the gate, and provided we've got space, then you can come in.
Hello, I'm Morgan Bell and I'm going to be talking to you tonight about the history of Cambridge Scientific Instrument Company, also known as the Scientific. I wrote this talk while I was Assistant Curator at Cambridge Museum of Technology, where I curated the permanent exhibition on Cambridge Scientific Instrument Company alongside former employees of the company. I've since moved on to the Whipple Museum of the History of Science, also in Cambridge, and it also has a Cambridge Instrument Company collection. So the images in this presentation are a mix of historic photos and objects from both of the museums. Unlike many university towns with science specialisms, Cambridge did not originally have its own scientific instrument makers. And before the 19th century, it was hard for academics to get the equipment they needed for their research. So in 1878, James Stewart, Professor of Mechanism and Applied Mechanics, set up a workshop to make equipment for his research. In order to fund his workshop, he also took commissions to make instruments from colleagues in other departments. This is one of them, a moving magnet reflecting galvanometer used to measure small changes in electric current, which was made for the Cavendish Laboratory. It's now part of the Whipple Museum's collections, and it's believed that this galvanometer was made by Robert Fulcher, who was Stewart's chief mechanic. However, within a year, Fulcher had left the workshop to set up his own instrument-making business in partnership with a man called Albert George Dew Smith. They moved to a workshop on Panton Street, and because of the demand for instruments, because it was so high, the business flourished. This is actually a later workshop, but you can see Albert George Dewsmith standing in the doorway of the workshop. Some of the instruments that Fulcher made were designed by Horace Darwin, so when Fulcher left the business at the end of 1880, Darwin took over, founding the Cambridge Scientific Instrument Company, known locally as the Scientific. A year later, it had outgrown its premises and the company moved to a new workshop on St Tibbs Row, shown in the photo. To replace Fulcher, Darwin and Dewsmith hired William T. Pye to run the workshop and oversee 3 mechanics and 2 boys. But Darwin was really the driving force behind the company, and his family always referred to it as Horace Darwin's shop. Horace was the son of Charles Darwin, and as a child he was interested in pretty much anything scientific. He studied maths at Trinity College, and after graduating, he did a 3-year apprenticeship at an engineering firm where he designed his first scientific instruments. This is the earliest known instrument he designed. It monitors plant growth, and Darwin made it in 1876 for his older brother Francis, who was Professor of Botany at the University of Cambridge. By the time Darwin founded the Scientific, he was a skilled designer and he developed many instruments for the Scientific. One of the early outstanding products was this rocking microtome, which cut biological materials into thin slices for examination under a microscope. Darwin's design in 1885 was not the first microtome, but improved earlier models due to its simplicity, accuracy, and robustness. Its simplicity meant it could be produced for a fraction of the price. This Darwin rocker from Cambridge Museum of Technology was made in 1895, and it shows the excellent design which remained unchanged until the 1970s. Early on, most of the company's instruments were for physiological or biological research at the university, such as an instrument for measuring frogs' hearts. For 2p each, the Scientific even supplied the frogs too. Darwin also worked closely with scientists who designed new instruments for the company to make. This Ewing extensometer, which belongs to the Whipple Museum but is on display at Cambridge Museum of Technology, is one example. It was the most important instrument designed by Professor James Alfred Ewing that the company made. It was an innovative design and it became the standard instrument for tensile testing, which is an important engineering test in which a sample is strained until it breaks. Research into new instruments increased in the 1890s, so the business once again outgrew its premises. And this is the purpose-built workshop on the corner of Carlisle Road and Chesterton Road that the company moved to. Because so many instruments were tailor-made for individuals, which was expensive, some years the company made a loss. In 1895 and 96, for example, the company incurred losses of £46 and £47. But when it did make a reasonable profit, such as the following year, Darwin distributed a share of it amongst his employees. Darwin was well liked as a manager. Bert Moore, a driver for the company who drove Horace to work, said, "He was, in every sense of the word, a true gentleman, and I'm very proud to have known him." Darwin was also well respected outside the company. He served as Mayor of Cambridge in 1896, and he was elected a Fellow of the Royal Society in 1903. When he died in 1928, 200 employees attended his funeral. However, going back to 1897, William T. Pye, the foreman who had replaced Fulcher, had received a 4.5% bonus in 1897 when the Scientific made a profit. But it wasn't enough to make him stay. A year later, Pye left the company to help his youngest son run an instrument-making business from his garden shed. This, of course, became the famous W.G. Pye & Company. Darwin was not happy about this new rival company, so in order to avoid a repeat, Darwin added a clause to the new foreman's contract saying that if he left the company in the future, he was to not set up business for the sale and manufacture of scientific instruments within 10 miles of Great St Mary's Church. Robert Stewart Whipple, who joined the Scientific earlier that year, took over from Pye as company secretary. As well as designing important instruments, he helped introduce new ways of working. He set profit targets, broadened the product range, and encouraged larger scale production. Whipple went on to have a distinguished career at the company. He became a director in 1905 and joint managing director in 1909. He also founded the Whipple Museum when he donated his personal collection of scientific instruments to the University of Cambridge in 1944. Whipple soon became the authority on temperature measuring equipment, which had become a key department for the scientific. Accurate temperature measurement is vital to many industries such as metalwork and food production. Instruments replaced human guesses, improving efficiency and making metalwork cheaper and food safer. Whipple designed this temperature indicator for industrial use in 1902. It was used with thermometers to give temperature readings. Importantly, it could be placed away from the thermometer, meaning it could be installed in a convenient location to save time and prevent workers disturbing readings by opening rooms and furnace doors. In the 1904 catalogue, the company explained, "At the cold stores of the Cardiff Pure Ice and Cold Storage Company Limited, in which we recently installed 34 thermometers, the engineer reads the temperature of all the rooms in 10 minutes. Before the installation of the electrical thermometers, the same operation took him 55 minutes. As the readings are taken 8 times in 24 hours, the time saved amounts to 6 hours a day." So you can see the impact of the company's industrial equipment. To order instruments and thermometers, customers use code words, some of which are quite amusing. So this is the 1904 catalogue. For general test work in boilers and engineering works, the company recommended purchasing a Whipple temperature indicator with thermometer number 128T and 3 yards of flexible lead. This outfit costed £28, 4 shillings and 6pence and had the code name Handcuff. With its move into industrial instruments, the company's sales increased and it expanded once again, building new workshops. By 1914, it was a major employer in Cambridge and was known nationally for its excellence. When the First World War started, the company's directors worried that business would slow down, but this never happened. In July 1915, the Scientific was made a controlled factory, meaning it can only do government-approved work. It designed and made instruments for the military and munitions factories for the rest of the war. One of the most important instruments it made for the military was the Gas Permeameter, which measured the leakage of gas through the fabric of airships. Dr. Gilbert Arden Shakespeare from the University of Birmingham designed it, but because demand was so high, the company stepped in to produce it on a larger scale. This one in the photo was used at RAF Cardington in Bedfordshire. The company also supported the war effort through producing industrial instruments for munition factories and other war industries. This photo shows a Wanner optical pyrometer being used in a foundry to measure high temperatures. After the war started, German instruments couldn't be imported, so Sheffield steel manufacturer Hadfields asked the Scientific to reproduce the optical pyrometer. The company designed this model and put it into production within 2 months. It was used in munitions factories throughout the country to monitor manufacturing processes. In order to keep up with increased production, the company built new workshops and a secret factory and a roller skating rink. It also hired women to replace serving men. At the start of the war, only 5 women worked at the company. By 1918, 200 of the 488 employees were women. In 1916, employees worked 53.5 hours a week. Thankfully, the company reported that little overtime was worked because it was bad both for the workers and for the work. In November 1917, the hours were reduced to 49.5 hours, but weekly wages stayed the same. Employees were paid in coins, which the paying out clerk poured into their hands from wooden cups. After the war, director Horace Darwin was knighted for his and the company's important contribution to the war effort. Managing director Cecil Mason was also awarded an OBE for his work making and testing fuses for artillery shells. Unlike elsewhere, women stayed at the company after the war ended and continued to be a valued part of the workforce. Women worked across most departments, and some, such as the wiring department and the photographic department, were mostly women. However, few worked in senior roles. The Darwin family ran the company for most of its history, including men who'd married into the family, but never Horace Darwin's daughters or granddaughters. The years following the war continued to be eventful. In 1919, the Scientific took over R.W. Paul Instrument Company and its London factory, and this is its entrance in Muswell Hill. The firm changed its name to Cambridge and Paul Instrument Company before shortening it to Cambridge Instrument Company in 1924. Its new logo was a mechanical piece called a cam, enclosed by an electrical circuit called a bridge. This represented the company's mechanical and electrical products and its birthplace of Cambridge. The company set up a non-contributory benefit fund for the employees the same year. It granted pensions, assistance to widows, and sick pay. Later, at the request of employees, to get rid of the feeling that it was a charity, employees over 18 contributed a penny a week. The company also set up a surgery with a full-time nurse in 1927. Some of the employees worked with dangerous substances. Violet Payne recalled packing thermometer sheaths in strings of asbestos and balls of mercury rolling around the workshop. Later, in the 1950s, old Walter used to stick his finger in the chemical baths in the plating department and taste the chemicals to check they were okay. Eventually, his teeth fell out. However, compared to many other industries, Cambridge Instrument Company was relatively safe to work at. The accident reports from 1915 to 1938 show only 1 or 2 accidents a year, and they were mostly hand injuries. For example, on the 23rd of June 1928, James Arthur Sands, an apprentice instrument maker, had his fingernail torn off while boring a hole in a spring washer in Machine Shop C. The Apprentice Trade School had been set up in 1917 to give boys a technical education and provide the company with the skilled instrument makers it needed. Apprentices usually continued working at the company, and many went on to hold important posts. The company valued its employees, and many progressed through the ranks. Arthur Wolfe, for example, started working at the company at age 14 as a clerk in the accounts section. He worked his way up and ended his career as chief accountant and company secretary. Before the Second World War, the company had 800 employees, 126 of whom had been at the company for over 25 years. When the Second World War started, the company once again made equipment for the war effort. These included instruments to measure the rate of aircraft deceleration, test the porosity of parachute fabric, and measure the tautness of the belt around a tank's wheels. This photo is of a Cambridge stereo comparator, which was used to analyse aircraft photos. It's part of the Whipple Museum's collection, but it's now on display at Cambridge Museum of Technology. In addition, the government installed hundreds of the company's index thermometers on British warships, such as cruiser HMS Euralius, which took part in the Allied invasion of Italy. They also made luminous dials for aircrafts. As the luminous paint was radioactive, the mostly female workers had to do their work underneath glass to protect them. Later in the war, one employee, Olive Spinks, recalled that they also had to remove the luminosity from the dials of planes that had crashed because the paint was too expensive to waste. This instrument was one of the most important pieces of equipment used to demagnetize ships and protect them from magnetic mines. The company received its first order from the Royal Navy on the 15th of February 1940, and by the end of the war, most Allied ports were fitted with the equipment. The company also trained naval officers and civilians to repair the flux meters. The company also improved sound ranging equipment to locate enemy artillery. In September 1944, the company sent a skilled team to Canterbury to set up and maintain these shell wave plotters for locating doodlebug flying bomb launch sites. One of the employees, Monty Cousins, described seeing his first doodlebug in Canterbury in his diary. He wrote, "They travel very fast and have a sheet of flame at the tail, driving them forwards at terrific speed." He and other instrument makers worked long hours, often 14 hours a day, without a day off for weeks. They also struggled to keep their plotting table up to date due to quick military advances in France. The team was originally meant to set up this sound ranging equipment in Belgium, but in the end they trained army personnel to do it. This turned out to be a really lucky escape for them, as the army personnel were all taken prisoner during the task. So for the rest of the war, the company team sent them food parcels. Not all the company's instruments were successful, however. In late 1944, the government asked the company to make a parachute opening device for a man who was unconscious. The company made it and tested it on the ground successfully hundreds of times, but it failed to open on its first drop from a plane in 1945. The war affected all parts of the company's operations. There was often lunchtime entertainment for employees, but most other social activities, such as lectures, sports events and dances, were paused during the war. Driving was particularly difficult, with blackouts, fogs and warnings, and it could also be dangerous. One evening, driver Bert Moore had only just passed through Coventry an hour earlier when it was bombed. To protect its employees from bombings, the company added a basement to Shop K to be used as an air raid shelter. Bunks were also installed for fire watchers and the Home Guard. They were responsible for sounding the alarm if bombs dropped nearby and fire watching from the canteen roof. Sleeping quarters for the Home Guard were originally in Shop E, which was where the mercury and luminous paint were used, making it a less than ideal place to sleep. After the Second World War, Cambridge Instrument Company returned to making industrial equipment and developing new instruments. Demand for the company's industrial equipment boomed as Britain and other countries restarted and re-equipped their peacetime industries. In 1947, the company had 150 orders a day, compared to their pre-war average of 60. However, it struggled to find materials and skilled employees. To solve this problem, the company found substitute materials and developed simpler manufacturing techniques. The company found creative solutions to other problems it faced too. In 1947, coal shortages and a harsh winter led to restrictions on electricity, so the company used tractors to drive machinery through line shafting, which allowed production to continue. The company soon expanded its workshops to meet increased demand and bought another factory in London. The company's magazine later described the Finchley site as very much the young brother of the Cambridge Works family. It became the production centre for mechanical thermometers and pressure gauges. In mid-1952, the company reported it had over 100 employees at the Finchley Works, many of whom were women. In the 1950s, the company expanded its apprentice training school and extended the length of the programme. The company's 1962 apprenticeship brochure boasted it was the gateway to a career in instrument engineering. Craft apprenticeships were for boys aged 15 to 17. They were very competitive, and Cambridge Instrument Company only accepted the best candidates. Each boy then had to pass a 3 to 6 month probation. The company stated, if the young man proves to be of the right calibre and wishes to continue, he's accepted for the 5-year course. The apprenticeships included both practical and theoretical training. The first year was spent learning how to use basic hand tools and machines, and each apprentice made their own set of tools. This is former apprentice Derek Pickett talking about making the tools.
Unlike some training courses, we didn't just use tools and make test pieces. Every single thing we did was a tool that we could use later on. The tool we made more or less at the end of the 6 months was a surface gauge, and that was instigated because it combined a whole range of skills that we learned during the 6 months. During each tool we made, it used to be assessed for accuracy at various stages, and if it was not acceptable, you were told it was not acceptable. So you learned that, quality was important, and basically that stayed with you evermore.
For the next 4 years, apprentices rotated between departments, learning what each one does, contributing to factory production, and learning what kind of work he was best suited to. The foreman of each department set up the apprentices' work, and there was always an experienced instrument maker available to help the apprentices and provide encouragement. The school produced some of the finest instrument engineers in the country. A Cambridge Instrument Company apprentice won first prize in the Physical Society's competition for apprentices 11 years in a row. This is Edgar Stern with his prize-winning cathetometer in 1958. When Glyn Jackson won the prize in 1963, the judges said his galvanometer was an excellent example of traditional electrical instrument craftsmanship. No fault could be found with the details. Apprentices usually continued working at the company, and many went on to hold important posts or work on innovative instruments. Monty Cousins, for example, started as an apprentice in 1917 at age 14 and a half, and he had a long and successful career designing instruments. When he retired in 1968, he said that designing many and varied instruments was his most satisfying memory, and even though he was retiring, he still felt a part of the firm. Sports and social activities played an important part of work life. They included football, cricket, badminton, rowing and angling. The Sports and Social Club organised outings and an annual summer sports day, which rotated between Cambridge, Muswell Hill and Finchley. At Christmas, there was a dinner dance for employees and a Christmas party for children, where Father Christmas gave out handmade presents. He also arrived on an exotic form of transport made by employees, such as a dragon or a Dalek. In 1959, the company also built a new research block on Chesterton Road to develop more new products. It was opened by Lord Adrian, Vice-Chancellor of the University and Master of Trinity College. For the ceremony, the company reserved a parking space outside the building for his limousine. When a frail old man parked his bike in the spot, someone was just about to ask him to move it before everyone realised it was Lord Adrian himself. The company made over 2,000 instruments at this time. One sales representative said their purposes ranged from recording the heart sounds of an unborn child to the problem of reducing gas consumption in a crematorium. The company was also known for its quality. When power stations switched to Celsius in the 1960s, engineers from across the country sent in their Fahrenheit instruments for conversion. One employee commented, "It soon became evident from the serial numbers and patterns received that there are a lot of really old instruments still doing a useful job of work. This is a real tribute to the quality of the work turned out in Old Shop E at Cambridge where the instruments were made. This is the sort of performance that built up the company's reputation. But the thought strikes me that if all our products lasted as long, business might be a little slow." Temperature measurement continued to be a key department for the company, and as well as in factories and foundries, its instruments were used in hospitals and on animals for medical research. This small animal temperature measuring outfit was primarily used on rabbits for pyrogen tests, which analysed foreign substances that cause fevers. The set of thermocouples were inserted into the animal's rectum to measure its temperature, and the sensitive spot galvanometer indicated the results. The company advertised that the thermocouples offered maximum comfort to the animals because they had blunt ends with soft plastic coverings. The most outstanding instrument of this period, however, was the electrocardiograph, which records the electrical activity of the heart. When Dr. Willem Eindhoven invented it in 1903, the machine filled a room, weighed 650 pounds and took 5 people to operate. However, it revolutionised the study of the heart and heart disease treatment. Dr. Eindhoven contacted Cambridge Scientific Instrument Company and proposed the company manufacture a commercial version. The company redesigned the instrument, reducing its size, but it was still very large, and patients had to immerse their limbs in stoneware vessels of salt water. The company started producing this model in 1911. However, because the early electrocardiographs were so large and immobile, patients had to be brought to the machine rather than taking the machine to the patients, and this was often inconvenient. In Cambridge in 1916, Addenbrooke's Hospital, at its old site on Trumpington Road, used the electrocardiograph at the university's pathological laboratories over a mile away. The connecting wires were carried on telegraph poles across town. There was widespread demand for a more portable and user-friendly model, and the company worked to improve the machine and make it smaller. However, it remained essentially unchanged for decades. Finally, in 1936, the company introduced a new portable model that packed into a suitcase. And then in the 1950s, it introduced two radically redesigned and even better models. This one from 1950 is called the Electrite, and it was the first valve-operated electrocardiograph in the UK. It was also the company's first direct writing instrument. Earlier models recorded onto photographic paper, and the results needed to be processed before analysis, often away from the consulting room in hospitals. The new direct writing model gave instant results. It was very well received and it sold well. When the Queen visited Cambridge in 1955, the mayor presented her with one. In 1958, the company introduced the Transrite, which was the first fully transistorized battery-operated electrocardiograph in the world. The Transrite was 12.5 inches long and weighed 20 pounds, which was much smaller and much lighter than the portable and the Electrite before it. Its new design also made it more reliable and robust. So in 1959, a British expedition took one to the Himalayas, showing exactly how portable and robust it had become. Later versions were also designed to be used in higher temperatures, so they could be exported to hot countries like India. A prototype of the Transrite 3, released in 1962, was tested by baking it in an oven for 2 hours. The knobs became too hot to touch, but it still worked. Not all the company's experiments were well received, however. After the company introduced a grey Transrite cover with red piping on the edges, they received a complaint from an angry doctor saying he couldn't go and visit a dying patient carrying a gaudy machine that looked like a picnic case. Plain grey became the standard following this complaint, but other colours were available for foreign markets. In the 1960s, every electrocardiograph the company produced was tested on their standard patient, Erkey brand. A copy of the test record was included with the instrument, so the characteristic rhythm of his heart became known to thousands of doctors around the world. And I'm going to play you a clip of an oral history with Jack Folds talking about Erkey brand.
One of the things about the cardiographs is that everyone was individually tested before it went to the customers. And we had a man there whose job it was to go to sleep. And when the cardiographs were ready for testing, he used to go into this cubicle and he would rest. Because one of the things about having an ECG is that you should be as relaxed as possible. So going to sleep is wonderful. And he went to sleep.
In 1958, the company had recruited a new, younger managing director called Harold Pritchard, and he changed the way the company operated. Pritchard realised that although the company had skilled instrument makers, it didn't have enough resources to research and develop new products. Instead of only developing instruments in-house, he encouraged the company to buy the rights to make innovative products invented elsewhere. In particular, he wanted something large that used new technology to reinvigorate the company and modernise its image. Dr. Peter Duncombe developed the precursor to the scanning electron probe X-ray microanalyzer at the University of Cambridge's Cavendish Laboratory as part of his PhD. It analysed the structure and composition of materials on a microscopic scale. In 1957, Dr. David Milford, a metallurgist from Tube Investments Research Laboratories, brought in a tiny piece of steel from a cracked boiler tube for him to examine. Dr. Duncombe almost turned him away because he'd finished his experimental work and he was writing up his thesis, but he changed his mind just as Dr. Milford was leaving. Dr. Duncombe's instrument produced images of the sample that were so impressive that Tube Investments decided to build an instrument for their own use. Dr. Duncombe and Dr. Milford collaborated on its design over the next few months. They produced the sketch of the complete instrument on Christmas Day 1957, much to the disapproval of their families. The prototype was then built at Tube Investments Hingston Hall workshops. It was a truly local, high-tech development and the result of a successful collaboration between the university and industry. There was substantial interest in the instrument from companies who wanted one, so Pritchard went to see it and Cambridge Instrument Company agreed to make it commercially. The company began producing it in 1960 as the Microscan. It was an immediate success, selling 83 over the next 5 years for £18,000 each, which is about £380,000 today. It was partly responsible for the company's record export turnover in 1960, which was 47% higher than the previous year. Customers included atomic energy authorities, steel companies, and research laboratories. The one at Cambridge Museum of Technology was the 13th made, and it was sold to glass manufacturer Pilkingtons, who used it to pioneer the float glass process. The Microscan was replaced in 1964 by the Geoscan, which had wider use. Company employees worked on it, making, remaking, testing and adjusting components right up until the last minute. Jane Killingworth only had 20 minutes to learn how it works before leaving for Germany to demonstrate the Geoscan at an international exhibition. The Geoscan was more complicated and therefore more expensive to produce than the Microscan, but it also sold well, and it was even used to examine the first moon rocks brought back by Apollo 11. A few years later, the company applied its new expertise to produce a similar instrument with better resolution and accuracy. Charles Oatley had been working on scanning electron microscopy at the University of Cambridge's engineering department since 1948, and he'd developed an instrument. Like with the Microscan, Harold Pritchard arranged for Cambridge Instrument Company to produce it under license. It was named the Stereoscan after the stereoscopic or 3D images it produced, like this one of a fly's eye. And I'm going to play you a clip of David Kynaston talking about Gary Stewart, who was one of Charles Oatley's students and led the production of the Stereoscans at Cambridge Instrument Company.
And Gary had worked in the engineering labs, and he went to he then joined the Instrument Company to actually make practical and possible the scanning electron microscope. By that time, everyone knew he could do it, because Charles had proven that. But Gary had to actually make it possible to produce an instrument that could be used by anyone for a particular purpose. And the feat wasn't just all about a scanning electron beam, it was about what you could do with it. And without that skill level that he tapped into in Cambridge Instrument Company, it would never have been possible.
The Stereoscan was officially launched in December 1965. It was the first commercial scanning electron microscope in the world. In 1966, it was named one of the 100 most significant new technical products of the year, and the following year, the company won a Queen's Award to Industry for technological innovation in a scanning electron microscope. The Stereoscan became an established tool for many fields of research, particularly for failure analysis and the development of new materials. British Rail used a Stereoscan to analyse cracks in rails and wheels, which saved people's lives. And Chester Beatty Institute researchers also used one to make the first 3D observation of a cancer cell at high magnification. These new electron probe instruments sold well, but they were really expensive to make. The company never made huge profits, even if it was renowned for its innovative and reliable products. At this time, the government was encouraging mergers to make industries competitive. Cambridge Instrument Company had itself expanded in the 1960s by taking over other scientific instrument makers. But in April 1968, it was the other way around, and the Rank organisation made an offer to buy the company. Cambridge Instrument Company's board was receptive to a takeover, but they thought technologically they, meaning the Rank organisation, could contribute nothing to Cambridge. Instead, they approached leading instrument maker George Kent about buying the company. This led to a heated bidding war for the company, which the Rank organisation was winning until the government intervened and bought shares on behalf of George Kent. The Rank organisation conceded the fight. This was the first time the government had taken sides and used taxpayers' money like this, which was very controversial at the time. With further government support, George Kent completed the takeover of Cambridge Instrument Company in June 1968. They had paid over £14.5 million for a company worth just £3.5 million. There were no layoffs, but George Kent imposed changes in management style. Many employees missed the family atmosphere and left the company. From the 1970s, parts of Cambridge Instrument Company were sold off. Other parts continued to thrive and develop more innovative products, but they were eventually sold off too. However, even today, remnants of the company still exist in Cambridge, in Zeiss and Leica. And Zeiss still makes modern versions of the stereo scan, such as this scanning electron microscope called the Sigma 300 VP. So I'm ending my talk here with these photos of exhibitions where you can learn more about Cambridge Instrument Company. Cambridge Museum of Technology is now open and it has a permanent exhibition on the history of the company. The Whipple Museum will not reopen until later this year, but when it does, it currently has a temporary exhibition about Robert Stewart Whipple, which features Cambridge Instrument Company objects. And if you're listening to the live talk tonight, I will be answering questions.